work for the oxygen reduction reaction. So this work will be divided in 4 parts, as you can see here. But first, let's start with the introduction. The rapid growth of population and the development of industries have led to the increase of energy demand, but as well cause serious threat to our health and our environment, leading us to try to find other solutions, but other than using traditional energy sources. So how do we find solution? If you ask any average person in the street, they will probably bring up renewable energies such as solar or wind energy, where they do like create less greenhouse, but they still emit some of dioxide of carbon. On the other hand, fuel cells is a totally clean device that generates electricity by electrochemical reaction. So at this device, there are 2 main reactions that happen, at the anode and the other one at the cathode. For the cathode one, the reaction is called the oxygen reduction reaction, also known as ORR, and represents the major concern of the reaction due to the several possible transformations that happen at the reaction, and as well for the oxygen breaking. So usually to tackle this issue, we use catalysts, mainly noble catalysts such as platinum. However, platinum here is located at 90% at the cathode, because the cathode here has the sluggish of the kinetic reaction. But the problem with platinum is that it's very expensive and represents, so it's very a high cost. But as well, using PT here leads to the poor stability, low efficiency, and as well methanol poisoning. So the methodology in this work will be divided in 4. First of all, we're going to prepare the precursor, which is ZIF, followed by catalytic presentation as follows, characterization such as XRD, BET, or TEM, and they're going to finish with electromeasurement. So ZIF here was chosen due to the porous structure, mostly the microporous structure, which can offer a higher density of the active sites. So the problem here with preparation of the iron nitrogen carbon catalyst is it's time-consuming, and as well it's very tedious, and sometimes it's also required 2-step pyrolysis and acidic leaching. Other challenges here, we can, as I said before, ZIF has a very microporous structure, which limits the diffusion of the reaction and the accessibility of the active site. But as well, it is difficult to achieve a uniform dispersion of the active site on the structure, but as well to have a higher durability and activity. So the innovation of this work for the fabrication of iron nitrogen carbon here is the introduction of the sulfur source to modify the electronic structure, and as well the employment of additional ligand in ZIF structure. I want to emphasize here that this work has never been reported before, as there are some work that report the use of ZIF that have been doping on sulfur, but no one has reported yet the heterodoping in ZIF derived from dual ligand. So the preparation of the catalyst is quite simple. So here, in addition of the traditional methyl imidazole for the formation of ZIF, we add undicyl imidazole as an additional ligand and linker to link the zinc and iron ions together to form this kind of a bridge. And we use sera as a sulfur source to modify the electronic structure. So to be clear, 4 catalysts were prepared. So first of all, we have the traditional one without sulfur or any doping or anything else. The second one, we doped with sulfur. The third one, we use only the additional ligand. And finally, the fourth one, we use both additional ligand and sulfur. So we can see through the XRD here on your left before the pyrolysis that the addition of sulfur and ligand did not influence on the crystal structure of our compound. After pyrolysis, we can see that 2 peaks appeared at 25 and 43 here, which due to the derived, partially converted into graphitic carbon. For the Raman spectroscopy, we have 2 peaks ascribed to D and G band, and we can see that the decrease of the intensity of G compared to MU to M and MU indicate the improvement of the graphitization degree. As well, on your right, we can see the increase of graphitization degree generate larger carbon planes. The TEM pictures here shows that our compound without sulfur or additional ligand has the typical shape of ZIF. After the addition of the additional ligand, the shape became more oval. But in the third one, the last one, sorry, the catalyst containing sulfur and additional ligand was able to recover its typical structure of ZIF. The PET surface area was investigated, and the isotope here showed the coexistence of micropores, mesopores, and as well mesopores. We can see, like here, for the MS, the introduction of sulfur led to the increase of micropore here, while the addition of indicylimidazoles had led to the formation of narrow mesopores. As well, the larger surface area shows here that the addition of both ligand and sulfur led to the increase in surface area exceeding 1100. XPS was as well investigated here, and we can see that the addition of sulfur and dual ligand had led to the increase of the active site iron nitrogen, reaching 18%. In addition, penitic anhydride was the main species for our compound, which can provide a coordination for the atom to form our structure. As well, two peaks here, two phenolic for the XPS here are recognized to be the active sites for the oxygen reduction reaction. The ICP was as well tested, and it shows the increase of iron content in our catalyst to reach 4.6%. The electrochemical measurement was tested as well, and we can see that the catalyst, our targeted catalyst, shows a better activity than platinum here, and as well a higher GK value and a smallest TFOS plot, which indicate the increase of kinetic activities. The calculated electron number here shows a perforated 4 electron number, and as well peroxide yield always below 9%, and to be always below 3% for the for targeted catalyst. As well, the materials show a better stability than platinum and a better methanol tolerance. So we can see through this work that the S-doping has led to the improvement of electronic structure of our catalyst, and the introduction of dual ligand has led to a richer micropore structure and open structure. So both of them, the S-doping in addition of dual ligand, has led to influence the carbon structure, which led to the higher density of active sites, which can explain to the improvement of the oral catalytic activity. So in conclusion, we were able to provide a simple method for the preparation of the ZIF derived from dual ligand with the typical ZIF shape, and the opulent catalyst showed a very impressive OR activity, better than our platinum, and as well longer durability. So this work was published in this Journal of Colloid Interface Science. Thank you.